Welcome to The Explainer. Today, we are diving deep. We're going to pull back the curtain on one of the most fundamental secrets of artificial intelligence, how a machine actually truly learns. So, you ever just stop and wonder, how does an AI, this really complex web of artificial neurons, actually learn anything? I mean, how does it go from making totally random guesses to predictions that are just shockingly good? Well, the answer is kind of weird. It's a little bit backward. Yep, you heard that right. Before an AI can even think about being correct, it has to become an absolute master at measuring exactly how wrong it is. And that measurement, it has a special name. It's called the loss function. Think of the loss function as the AI's reality check. This isn't just a simple pass or fail. Oh no. It's a super precise measurement of the gap between what the model guessed and what the actual truth is. The bigger that gap, the higher the loss score, which is a big red flag for the AI that, hey, you need to make a much bigger adjustment. Okay, so let's frame it this way. The loss function is the official scorekeeper in the big game of machine learning. Its one and only job is to watch every single guess the model makes and slap it with a penalty score. So the really crucial thing to get here is that this isn't some vague oops, I was wrong feeling. It's a hard number. It is the cold, calculated mathematical distance between what the model thought was going to happen and what actually did. And the process itself, it's actually pretty elegant. Step 1, the model makes its best guess. Then, step 2, the loss function swoops in, compares that guess to the real answer, we call that the ground truth, and it spits out a single number, the loss score. The higher that number, the worse the guess. Simple as that. But here's the thing, you can't measure every single problem with the same tool. It just doesn't work. As an AI architect, one of your first, and honestly, one of your most important decisions is choosing the right ruler for the job. So broadly speaking, machine learning tasks fall into two big buckets. You've got regression, which is all about predicting a number on a spectrum, like a price or a stock value. And then you've got classification, which is about picking a category, like, is this a cat or is this a dog? And guess what? Each one needs its own special kind of loss function. Let's look at a regression example. Let's say we trained an AI to predict YouTube views. As you can see, some of its predictions were, well, way off. For that perfect cold brew video, it was off by 40,000 views. That's a huge miss. The loss function's job is to take that massive gap and turn it into a really painful penalty score. Now, the most common ruler for this kind of job is called mean squared error, or just MSE. It finds the difference for each guess, squares that difference, and then averages all of them out. And that one simple move, squaring the error, is everything, because it gives this function a very, very specific personality. And that squaring action, it basically makes MSE a total perfectionist. Being off by, say, 2 gives you a penalty of 4. But being off by 10, whoa, that gives you a penalty of 100. It absolutely despises big errors, and it will force the model to obsess over avoiding those huge, embarrassing screw-ups. All right, so what about those classification tasks? We're not measuring a numerical distance anymore. Here, it's all about confidence. An AI doesn't just guess cat. It actually assigns probabilities. It might say, I'm 95% sure this is a cat. The go-to loss function here is cross-entropy, and it's built specifically to measure how well those predicted probabilities line up with reality. Cross-entropy is all about punishing false confidence. It uses some clever math, logarithms, to create a penalty that just explodes. It goes through the roof. The more certain a model is about the wrong answer. So if a model says, I'm 99% sure this is a dog, but it's really a cat, bam, cross-entropy hits it with a massive penalty. It basically forces the model to be humble until it has every right to be certain. So we have this score, right? This number that tells us just how wrong the model is. But so what? What do you do with it? Well, this is where the magic really happens. That score isn't just a grade. It is the engine that drives all improvement. This right here, this is the training loop. First, data goes forward through the network and the model makes a prediction. Second, our loss function calculates that error score. And third, and this is the absolute key, that error signal travels backward through the entire network. It's a process called backpropagation. And it literally tells every single neuron how much it contributed to the mistake and exactly how it needs to change to do better next time. If you take one thing away from this, let it be this. The loss function provides way more than just a score. It creates a map. It literally points in the exact direction of less wrong. It's the thing that tells the learning algorithm, hey, to get a better score next time, you need to tweak your settings this way. Without that direction, all of AI learning would just be random guessing in the dark. And once you really get this, we can move from just using AI to actually designing it. Choosing a loss function is, in a way, like choosing a personality for your model. You are literally defining what the model cares about most. So beyond our little perfectionist MSE, you've got other options. Maybe your data is messy and has a lot of crazy outliers you just want to ignore. Well, you might choose mean absolute error, or MAE. It's more of a pragmatist. It's less sensitive to those huge errors. Or you could go for Huber loss, the compromiser, which tries to get the best of both worlds. Okay, now for a really fascinating twist. Up until now, we've been measuring wrongness against some fixed, known truth, right? But what happens when the goal is something way more abstract, like creating a brand new piece of art? Welcome to the mind-bending world of adversarial loss, which is used in models called GANs. What you have here are two AIs locked in this constant cat and mouse game. One AI, the generator, its whole job is to create fakes. The other AI, the discriminator, its job is to spot them. So the generator's loss isn't measured against a static truth anymore. It's measured by how well it can fool its opponent. And this relentless competition is what pushes the AI to become unbelievably creative. And that's really why the loss function is so incredibly important. It's not just a little piece of math in the code, it is the objective. It is the very definition of good that we hand to the AI. When we choose how we measure error, we're literally programming that model's values and its priorities. So I'll leave you with this to chew on. Think about a self-driving car. Is being 2 inches off the center of the lane the same kind of wrong as being 2 inches away from hitting a pedestrian? Of course not. The loss function you'd have to design would need to weigh those errors completely differently, making safety, thousands of times more important. And that choice, that specific definition of wrongness, that is where the true intelligence of the whole system actually begins.